Hello everyone and welcome to this online lesson on FET biasing. My name is Faiz and I will be delivering this online lecture. Okay, so let us first recap on what are the some of the general relationships of the current voltage relationships of all the FETs that we have studied so far. Now, for all FETs that we have studied so far, including the JFETs and MOSFETs, we know that the gate current is zero, and the reason is because the input impedance of all the FETs are very high. So the gate current is then negligibly small. So therefore, we can approximate the gate current to be zero, and this is also the reason why the FETs or field effect transistors are voltage control devices. And we also know that the drain current is also equal to the source current for all FETs. Now, the next relationship is that for JFETs and DMOSFETs, the drain current is governed by the Shockley equation. The drain current is a function of the IDSS, which is the drain saturation current, the applied gate voltage, and also the pinch-off voltage. Now, for eMOSFETs, the drain current is a function of the applied gate voltage and also the threshold voltage. And the drain current is given by this equation, not by the Shockley's equation. And for BJTs, we know that the base current and the collector current are linearly related. IC is equal to beta IB, but for FETs, the relationship between the input and the output is not linear. The input is VGS and the output is drain current. And as you can see here, there is a quadratic term in the transfer characteristic of the MOSFETs. So these are some of the common biasing circuits that we are going to be studying for JFET, DMOSFET, and eMOSFET in this lesson. Let's first have a look at the JFET biasing circuits. Okay, so the simplest biasing arrangement for the JFET is the fixed bias circuit. Now, the reason why it is called a fixed bias is because the bias that you apply at the gate terminal of the JFET is fixed by the DC voltage which is connected to the gate, which is this VGG DC voltage source. So for this particular arrangement of JFET with fixed biasing circuit, the gate current is zero, the drain current is equal to the source current, and also the drain current is given by the Shockley equation. So let's now do a simple DC analysis on the fixed bias JFET circuit. Now, for the purpose of a DC analysis, we can actually take out the gate resistor which is connected to the gate, and the reason is because the gate current is zero. So therefore, you will not have any voltage drop across the gate resistor. So we can just take it out during our DC analysis. So therefore, we are left with this circuit and this simplified circuit. So if you do a KVL around this loop around the gate source GS loop, you will find that the VGS is equal to minus VGG, which is this equation here. And if you do a KVL around the drain to source loop, you will find that VDD minus ID RD minus VDS is equal to 0. And if you arrange that equation, you will get this particular equation here. And since the source is directly connected to the ground, so Vs is equal to 0. So therefore, Vd is equal to VDS and Vg is equal to VGS. And the drain current is given by the Shockley equation. So the fixed bias JFET circuit can be analyzed very easily using either the mathematical approach or the graphical approach. So using the mathematical approach, you just substitute the magnitude of the applied gate voltage VGS with the magnitude of the DC voltage source which is connected to the gate terminal, and in this case VGS is equal to minus VGG, with the VGG being the DC voltage source here connected, which is connected to the gate. And from then you substitute the magnitude of VGS back into the Shockley's equation, which from then on you can get the magnitude of drain current, and after getting the magnitude of drain current, you can use it to solve for these other parameters here, including VDS, RD, and ID, and so on. So it's a relatively straightforward approach to solve a fixed bias JFET circuit using the mathematical method. The other way is by using the graphical approach, and to use this approach you first have to plot out the drain current characteristic, the transfer characteristic of the JFET using the Shockley equation, and from then you plot out what is the magnitude of the applied gate bias, in this case being VGS is equal to minus VGG, so that is this black line over here. So the intersection between your load line and your transfer characteristic, your drain current line, gives you your Q point, and from that Q point you can get what is the drain current at Q point, and using the magnitude of the drain current you can solve for whatever variables, whatever voltages that you are interested to find out in the circuit. Okay, so let us look at a very quick example on how to analyze a fixed bias JFET circuit. So this is example 7.1 in the textbook. So you are given a fixed bias JFET circuit, and you know the circuit is fixed bias because you have a DC voltage directly connected to the gate terminal, so it's fixed bias. And you are also given the parameters IDSS and pinch off voltage, and you are asked to determine the values of these parameters given here. So the answers are already given in the example, so you can check your answers if they are correct. So let's look at how we solve this question. So you start by plotting out the drain current characteristic of the JFET using the shorthand method. And in my previous lecture, I have explained in detail how to use the shorthand method to sketch the drain current, the transfer characteristics of the JFET. So if you are unfamiliar with the shorthand method, so please visit my previous lecture and familiarize yourself with the shorthand method on how to draw these blue curves. So once you get this drain current characteristic, you will draw another line of your load line, and that load line is just simply your applied gate bias. And your applied gate bias for a fixed bias JFET circuit, your applied gate bias is just equal to the magnitude of the DC voltage which is connected to the gate terminal. So in this example, your DC voltage is minus 2 volts. So you just plot out minus 2 volt on the same graph. So the intersection between your load line and your transfer characteristics gives you your Q point, and from that Q point you can read out the drain current at Q point. So using this value of drain current, you can then solve for VDS and whatever VDS, RD, and whatever parameters that you might be interested. So please try this example and check if you get the same answers as indicated in this slide here. The second biasing circuit that we're going to study for JFET is called the self-bias circuit. And this configuration of biasing eliminates the need for two DC supplies. And as you can see in the circuit here, you don't have the DC voltage source connected to the gate terminal anymore, and you replace that but what you have in as a replacement is a resistor in the source terminal of the JFET. So similarly, the same relationships hold for this self-biased JFET circuit. You have zero gate current, you have the drain current is equal to the source current, and the drain current is given by the Shockley equation. So let us now do a simple DC analysis on the self-biased JFET circuit. Let's start with the GS loop first. So if you do a KVL around the GS loop, you will find that the VGS is equal to minus ID times RS. So that's this equation here. So as you can see, the applied gate voltage is determined by the magnitude of the drain current and also the value of the source resistance. So this indicates that the applied gate bias is not static. It is determined by the magnitude of the your drain current. And also if you do a KVL around the drain to source loop, you will find that the magnitude of the VDS is equal to VDD, the voltage source, minus the drain current times the cumulative resistance of RD plus RS. So that's this equation here. And similarly, the self-biased JFET circuit can be solved either using the mathematical or the graphical approach. So let us look at how can we solve the self-biased JFET circuit using the graphical approach. So there are 3 steps involved, and the first step is you start by plotting the transfer curve of the JFET using the shorthand method. And to do that, you will need to find what is the value of IDSS and pinch-off voltage from the specification sheet of the JFET. So out of that first step, you will get this blue line here, and this blue line gives you what is the magnitude of drain current at any particular applied gate voltage. The second step is then you plot your load line, and that load line is given by this equation here. And as a result of that, you get that black curve over here. So the intersection between, in the third step, you find the intersection between the load line and your transfer curve. So the intersection between these two lines gives you your Q point, and that Q point is the simultaneous solution of your network load line and your transfer curve. And from that Q point, you can read out what is the applied the VGS at the Q point, and also the magnitude of drain current at the Q point. Let us try a simple example of solving the self-biased JFET circuit. This is example 7.2 obtained from the textbook. So you are given this JFET self-biased circuit, and the IDSS and the pinch-off voltage are given, and you are asked to solve for the you are asked to find, to calculate what are the following parameters. So the answers are given here, so you can try it out and compare your answers. So just like in the step which I have explained previously, you can start by plotting out either the transfer curve or the load line. In this example, we'll try out by plotting out the transfer curve first. The load line first. So the load line of the circuit is given by VGS is equal to minus IDRS. You obtain this equation by doing a KVL around the GS loop. So in this particular example, VGS is equal to minus ID times 1000, and that 1000 is actually the value of your source resistor. So it's basically just a simple line. It is a simple linear line, and the line is here. So you can just substitute for whatever value of ID you want, and then you get the corresponding VGS. So you'll probably just need about 2 to 3 points to plot the entire line, and this being a linear curve, and it starts from the origin of 0, right? And then you proceed to the next step, and the next step is that you plot the transfer curve of the JFET, and you can do this using the shorthand method by using the values of IDSS and VP that are already given in the question. So you plot it out using the shorthand method, and finally you superimpose the both of the curves together, and the intersection between the two curves give you your Q point, and that from Q point you can read out what is the VGS at Q point and what is the value of ID, the drain current at Q point. And using these values you can solve for VDS and other parameters which you are interested on. So that's how you solve that's how you analyze the JFET with the self-biased circuit. So next is the JFET with voltage divider bias circuit. And as you can see on the figure here, the circuit looks pretty much, in fact, exactly like the voltage divider bias circuit for the BJT, except that for a JFET, you have the gate current equals to 0. You have the drain current is equal to the source current, and also the drain current is given by the Shockley equation. So the way we analyze a voltage divider bias for JFET is exactly just like how we solve for the voltage divider for BJT. And looking at the diagram, you can see that the applied gate voltage, the V voltage at this point here, which is connected directly to the terminal on the gate terminal, is equal to the voltage drop across the divider resistor R2. So using the voltage division rule, you can find out what is the VG, which is just R2 divided by R1 plus R2, multiply the whole term by VDD. And from then you get your VG. And then applying the KVL around the GS loop, you will find that the VGS is equal to VG minus IDRS. So that's this equation here, and this equation is your load line. And then doing the KVL across the drain source loop, you will find that VDD minus IDRD minus VDS minus ISRS is equal to 0. You simplify that equation and you will get this equation right over here. And also you know that because the gate current is 0, so the current through resistor 1 is equal to the current through resistor 2. IR1 is equal to IR2. So therefore you can calculate that current just by using this simple Ohm's law here. VDD is IR1 is equal to IR2 is equal to VDD divided by R1 plus R2. So because R1 and R2 are in series. So the way you use the graphical approach to solve for the Q point of a JFET with a voltage divider by a circuit is similar to the way which we have learned for the other biasing JFET biasing circuits. And there are 3 steps involved. The first step is that you plot your load line, and for JFET voltage divider by a circuit, your load line is given by this equation here, which you can derive by doing a KVL around the GS loop. So you don't really have to memorize this. Just do a KVL around the GS loop and you get this equation here. And then the second step is that you plot the transfer curve of ID versus VGS, and you can plot this very quickly and very easily using the shorthand method. And finally you find the intersection point, and that intersection point gives you the simultaneous equation, simultaneous solution of the 2 equations, and also gives you the VGS at Q point and ID at Q point. And from using that values, you can solve for the other parameters that you are interested. Alright, so let's try a simple example on how to analyze a JFET transistor with a voltage divider bias. So this is example 7.4 from the textbook. You are given a circuit, a JFET circuit with a voltage divider bias. The parameters of IDSS and pinch-off voltage is given, and you are asked to determine these following parameters. So the answers are also given. You can try it out and compare your answer. So using the steps which I have mentioned just now, first you plot the load line of your circuit, and that load line is given by this equation here. VGS is equal to VG minus IDRS. And so you can plot it, very simply plot it by first setting the value of ID is equal to 0. So when your ID is equal to 0, your VGS is equal to VG. And that VG is actually the voltage at this point here, voltage at the node which is connected to the gate terminal, and VG can be found by using the voltage division rule. So setting out the ID is equal to 0 gives you VGS is equal to VG, and that is the point over here. So that's your first point. And the second point can be plotted by setting the VGS is equal to 0. So when VGS is equal to 0, ID is then just simply VG divided by RS. So you know your VG already from your voltage division rule calculation, and the value of RS is given in the circuit diagram. So you can simply calculate what is that the other point. So that other point is this point here at the intersection in the y-axis. So now you already have 2 points, so you can connect the 2 points together, forming a straight linear line. So that's your load line. This black line is your load line. And then you proceed to the second step, and second step is to plot the transfer curve of your JFET using the shorthand method and using the values of IDSS and VP given in the question. So the values are given here. So you plot that out using the shorthand method, and then you identify the intersection point between the load line and the transfer characteristics. So the Q point gives you your VGS, the magnitude of VGS at Q point, and also the magnitude of drain current at Q point. And you can solve for these other parameters. You can use the two values to solve for other parameters you are interested. So that's all for JFET biasing circuits that we're going to cover in this course. Let us now proceed to the D-MOSFET biasing circuit, the depletion MOSFET biasing circuits. So the first biasing circuit for D-MOSFET that we're going to study is the self-bias circuit. And D-MOSFET bias circuits are actually pretty similar to biasing circuits for JFET. And the only difference is that, and you already know this from previous lecture, that D-MOSFET can be operated with positive values of VGS, because D-MOSFET can operate in both the depletion mode and in enhancement mode. And in the enhancement mode, you will apply a positive value of the VGS. And the ID value, the drain current of D-MOSFET can actually exceed the value of IDSS. So it should look familiar to you right now. And the gate current, similar to JFET, the gate current is 0. The drain current is equal to source current, and also the drain current obeys the same law as a JFET. The drain current is given by the Shockley's equation, except that the magnitude of VGS for the D-MOSFET can be positive. So therefore, you can get a drain current which is much higher than the IDSS. So the way you analyze a D-MOSFET with a self-biasing circuit is also similar to how you analyze a JFET with self-bias, and you use the same 3 steps which I've explained to you previously. The first step is that you plot the transfer curve of the D-MOSFET using the shorthand method, and then you plot the load line, your load line, and in this case your load line for self-biased circuit is VGS is minus IDRS. So that's this black curve here is your load line. So the intersection between your load line and your transfer curves gives you your Q point. And also you have to take note that for a D-MOSFET, because the value of VGS can be positive, so in order to find what is the value when you apply a positive gate voltage, you can use the Shockley equation to plot that out. Okay, let's try a simple example of a D-MOSFET with a self-biased circuit. You are given a D-MOSFET, the parameters of IDSS and pinch-off voltage are given. You are asked to determine what is the values of drain current, gate source voltage, and drain voltage at Q point, and the answers are given here. Okay, so how you solve this is by using the same familiar steps which you have learned previously. So first you start by plotting out the transfer curve of the D-MOSFET using the shorthand method. So using that step, using that shorthand method, you will get this curve here when the applied gate bias is in the negative. But you also know that the D-MOSFET can be operated with a positive gate bias. So to calculate what is the point, what is the drain current when you apply a positive gate bias, you use the Shockley equation. So use this Shockley equation, you insert a positive value of VGS, and you will get the magnitude of current in the enhancement mode when the applied gate bias is positive. So this is the result of applying the first step, and the second step as well. The first step is plotting using the shorthand method to plot the values of ID when the applied gate bias is in the negative. The second step is you use the Shockley equation to find the magnitude of drain current when the value of VGS, the applied gate voltage, is in the positive. And the third step is you plot out the load line, and it's relatively simple to plot because it's just a linear equation starting from the origin, and then the intersection between these two lines, between your load line and your drain current characteristics, gives you your Q point, and you can read out what is the value of VGS and drain current at Q point. And finally, let's have a look at the voltage divider bias for D MOSFET. And again, it looks similar to that of the JFETs with voltage divider bias. You have two resistors here, and the gate current is 0, the drain current is equal to source current, the drain current is given by Shockley equation, and these are the parameters of the D MOSFET, IDSS, and V pinch off. Let's go over to to a quick example of to analyze a D MOSFET with a voltage divider bias. So you apply the same steps which you have learned before. The first step is that you plot the transfer curve of drain current versus VGS using the shorthand method, and this gives you this blue curve in the region where your VGS is in the negative. Your applied gate bias is in the negative. But you also know that the D MOSFET can be operated with a positive gate bias. So if you need to apply to know what is the magnitude of drain current with a positive gate voltage, you use the Shockley equation. So you just substitute the value of VGS with a positive gate voltage, and you get your drain current in the enhancement mode. So that's one point over here, operated at the positive gate voltage. So that's first and second point. And the third point is, the third step is that you plot your load line, and that load line is given by this equation here. You can derive this from doing a KVL around your GS loop. So VGS is equal to VG. VG is gate voltage, voltage at this node here, which is connected directly to the gate terminal of the D MOSFET, minus IDRS. And the VG can be calculated using the voltage division rule, which you should already be familiar. So it involves the using the value of the resistance coming from R1, R2, and also the voltage coming from your supply. So you find the intersection, and then you find the intersection point between your load line and your transfer curves, and that will give you your Q point. So please just try this example out. So the example calculation is shown here to find what is the value of VG, and also after finding the Q point, you can read out what is the value of VGS, Q point, and ID and Q point, and use that values and substitute that values back into your KVL equation around the GS loop or DS loop to find the answers of voltages or currents which you are interested to find. And we have arrived at the final part of this online lesson. We are going to be studying the biasing circuits for enhancement mode MOSFET. Let us first look at the voltage divider bias circuit for E MOSFET. And as you can see from the figure here, the biasing circuit for an E MOSFET, for a voltage divider bias circuit for an E MOSFET, looks pretty similar to, in fact, it's similar to JFETs and of the D MOSFET. So you can use the same procedure to analyze it. So you know that the VG, the voltage at this point here, which is connected directly to the gate terminal, is given by can be found by using the voltage division rule between R1 and R2, and also VDD. So that's this equation here. And if you apply a KVL around the GS loop, you will find that VGS is equal to VG minus IDRS, and this VG of course comes from the value that you have calculated using the voltage division rule. Similarly, if you apply KVL around the drain to source loop, you will get this equation here. And the only difference on how to analyze an E MOSFET with voltage divider bias compared to the biasing circuits which we have covered so far is that the drain current is given by this equation here. The drain current is not given by Shockley equation, but the drain current of E MOSFET is a function of the applied gate bias and the threshold voltage, and also some constant K which you can calculate. So the procedure to analyze an MOSFET with a voltage divider by a circuit is similar to the procedure which we have learned previously, except with minor alteration. And these are the steps involved. So you can start by calculating what is the value of K, and you need the value of constant K so that you can use it to calculate what is the value of drain current at any particular gate voltage. And of course sometimes the value of K is given in the question, but sometimes you are asked to calculate what is the value of K, and also the threshold voltage should be given in the question or can be obtained from the specification sheet. So you first find the value of constant K, and then you plot your drain current transfer characteristic of your MOSFET, and this is simply ID is equal to K multiplied by VGS minus threshold voltage squared. So that gives you this blue curve here. So this is your blue curve here, and as you can see, the drain current, the MOSFET starts to conduct once the gate voltage exceed the threshold voltage of the circuit. And in this example, I believe the threshold voltage of this MOSFET is around is a 5 volt, right? And then the third step is that you plot your load line, and that load line can be obtained by doing a KVL around the GS loop, and the equation is given here. So that plotting your load line gives you this black line here. So the intersection between your load line and your transfer characteristics of your MOSFET gives you your Q point. Let us now have a look at a simple example of how to analyze an MOSFET with a voltage divider by a circuit. This is example 7.11 from your textbook. So you are given an MOSFET with a voltage divider bias, and the value of the resistors are given, and also the values of the threshold voltage of the MOSFET is given as 5 volts. And also you are what is stated here is that when the applied gate source voltage is 10 volts, you get a drain current of 3 milliamps. So you can use this information to calculate what is the value of K, the constant K, and you need that value of constant K to calculate what is the value of drain current at any particular gate voltage that you are interested. And then you can use that to solve for the parameters that are asked here. So the answers are already given, so we can check the answers. Alright, so first step is you first begin by calculating what is the value of K, and the value of K can be found by applying this formula. So it's a function of ID on, VGS on, and the threshold voltage. These are all the values which are given in the question here. So you just substitute all these values back into the formula, you get the value of K, and using the value of K, you can then plot the transfer characteristics of the MOSFET. So the drain current is a function of K, the applied gate bias, and the threshold voltage. So you can plot probably 3 or 4 points of VGS. You can probably start from 5 volt to 10 volt to 15 and 20 volts. So put all of these values of VGS into the equation here to find what is the corresponding ID, drain current, and then you just connect all the points together. So as you can see, the threshold voltage is 5 volts. So before the applied gate voltage reaches 5 volt, the transistor should not be giving any current, it should be 0. And only after the applied gate voltage exceeds the threshold voltage of 5 volts, then only the transistor, the MOSFETs start to turn on and conduct drain current. So that's your second step. And the third step is then to plot your load line, and your load line is given by this equation here. It is formed by doing a KVL around the GS loop. So you just need 2 points to plot this load line here. And the first point is that you can find by setting the value of drain current equal to 0. So if you set your drain current is equal to 0, so this term here becomes 0, ID times RS becomes 0. So VGS is just simply your VG, and VG for this particular circuit can be found by using the voltage division rule. VG is the applied the voltage that you apply at the gate terminal of the source of the MOSFET, and you can find it by using the voltage division rule. And once you get that, So VGS is equal to VG when ID is equal to 0. So that's your point over here. And in this particular circuit, if you substitute the value of R1, R2 and VDD, you get your VG equal to 18 volts, which is this point here. And the other point that you need is you can plot it out by setting your VG equal to 0. So setting your VG equal to 0, you can get the value of ID. ID is just then VG divided by RS. Setting your VGS equal to 0. So setting your VGS is equal to 0, you get your value of ID is equal to VG divided by RS. So that's another point over here. And then we just connect these 2 points together, forming a straight line. And the final step is to identify the Q point. So the Q point is just simply the intersection between your load line and your transfer characteristics of the MOSFET. Alright, so this is your Q point. Your applied your VGS at Q point can be read out, and similarly your drain current at Q point can be read out, and you can use that value to solve for the magnitude of VDS. Okay, so the final biasing circuit that we are going to be studying for MOSFET is the feedback bias for MOSFET. So this is how the biasing circuit looks like. You have a gate resistor which connects the gate of the MOSFET to the gate terminal of the MOSFET to the drain terminal of the MOSFET. So the same relationship holds. You have gate current equal to 0, and because you have no gate current, therefore the voltage drop across the gate resistor is also 0. And also you note that because the gate is now connected to the drain, so VG is actually equal to VD because they are connected to the same node. And you use that equation, so that is the equation here. And when you apply this equation to a KVL around the DS loop, you get this equation right here. So you apply the same family steps to analyze an MOSFET with a feedback bias. You first have to calculate what is the value of constant K, which you will then need to use to plot for VGS versus ID, the drain current versus ID for any particular range of gate voltage that you are interested. So that's your second step, first step and second step. And the third step is to plot your load line, and load line is given by VGS is equal to VDD minus IDRD. So as you already know, then the intersection between this your load line and your drain current line gives you your Q point. Alright, so let's quickly have a look at this simple example of an MOSFET with a feedback bias. Example 7.10 from your textbook. So you have an MOSFET, and the parameters of ID at a particular VG is given, and also you are given the threshold voltage of the MOSFET. So you can use these values to calculate the value of constant K. And then you are asked to find these values of ID and VGS at Q point. Okay, so you apply the same family steps to solve for the MOSFET with feedback bias. And you first start by calculating what is the value of K using the values of the parameters given in the equation. So once you get the value of parameter K, you substitute that into the equation to calculate the value of current. So you try to find out what is for maybe 3 or 4 points to plot what is the value of ID at any particular applied VGS that you are interested. So step 1 and step 2 will give you the transfer characteristics of the MOSFET. So that is the blue line over here, right? And then you proceed to the third step. Third step is plotting the value, the load line of the for the circuit. So the load line is given by VGS is equal to VDD minus IDRD. So plotting this load line gives you this black line over here. You just need 2 points to plot this load line. You first find it by you find the first point by setting the value of ID is equal to 0. So when ID is equal to 0, VGS is equal to VDD. So that's 1 point over here, right? and then the other point you find by setting the value of VGS is equal to 0. So setting value of VGS is equal to 0. ID is just simply VDD divided by RD. So that's another point over here. Right, so you connect the 2 points together to form your load line, and the intersection between your load line and your transfer characteristics give you your Q point, and from which you can read out the answers for VGSQ and for IDQ, and these are your answers for this particular question. Right, so far we have been using n-channel FETs as an example for discussion and calculation, but you also know that p-channel FETs apply the same calculations, the same methods, and the same procedures for analysis, except that the voltage polarities and the current directions are the opposite, and therefore the graphs also will be mirroring to that of the n-channel graphs. So these are some of the practical applications of the MOSFETs, of the FETs that we have learned so far. A FET can be used as a voltage controlled resistor, and the way you control the value of the resistance of the FET is by varying the value of applied gate voltage, the VGS. And in your textbook, these other examples are also explained, where a JFET can be used as a voltmeter. It can be used in a timer network and in a fiber optic circuitry, and also you can use a MOSFET. One of the common application of a MOSFET, of a power MOSFET, is that you can use it to function as a relay driver. Okay, so let's have a look at a practical example of how a MOSFET functions as a relay driver. So the idea is that you use the MOSFET to drive a high-powered system without drawing power from the driving circuit, without driving power from the input from the source. So in this example, you have a MOSFET, and that MOSFET is connected to a relay, and that relay drives a high-powered or high-voltage system. And this can be an alarm, a lamp, a heater, a fan, or motor, or whatever. But as long as it can be, as long as it is high powered, right? And on the input side of the MOSFET, you at the gate terminal you have the photoconductive cell, which is basically a light sensor, and the resistance of this light sensor changes with the amount of light that it is being exposed to. So when the sensor receives a lot of light, the resistance of the sensor will go down, and as a result the gate voltage, the VG, will also be very low, and as a result of this low VG you will not get any drain current, so then it will not turn on the light or the alarm or the fan or whatever on the output side. But when you get a very low light amount of light being exposed to the light sensor, the resistance of the photoconductive cell goes up, and as a result of that, if you use a KVL, you use the voltage division rule. When the resistance of this part here goes up, the VG will similarly go up, and the increase in VG will draw more current from the voltage source, and as a result you get some drain current, and that drain current will turn on the relay, and that relay will drive your fan, your lamp, and or any other high powered system. So this is a simple example of how a MOSFET can be used as a relay driver. So with that, that concludes my online lesson on FET DC biasing. So I hope we have gained some benefits from this online lesson. If you have any question, please ask me during our class time, and please try. I want you to try to solve these problems at the end of chapter 7. Just 5 questions, and we are going to discuss the solutions during our tutorial session. So that's it. Thank you very much. Bye bye.